an improved method of automated non-parametric content analysis for social science. Abstract. Some scholars build models to classify documents into chosen categories. Others, especially social scientists who tend to focus on population characteristics, instead usually estimate the proportion of documents in each category, using either parametric classify and count methods or direct non-parametric estimation of proportions without individual classification. Unfortunately, classify and count methods can be highly model-dependent or generate more bias in the proportions even as the percent of documents correctly classified increases. Direct estimation avoids these problems, but can suffer when the meaning of language changes between training and test sets or is too similar across categories. We develop an improved direct estimation approach without these issues by including and optimizing continuous text features, along with a form of matching adapted from the causal inference literature. Our approach substantially improves performance in a diverse collection of 73 datasets. We also offer easy-to-use software that implements all ideas discussed herein. Introduction. Scholars from a variety of fields have worked on improving the automatic classification of individual objects, where the unit of interest might be a web page, war, person, document, country, social media post, etc. Social scientists use classifiers too, but they more often focus on aggregate generalizations about populations of objects, such as the percent in each category, rather than any one individual classification, a task that is sometimes called quantification. Indeed, a plausible case can be made that one of the defining characteristics of social science is a focus on population-level generalizations. We discover an interesting puzzle about one election, but try to develop theories that apply to many more. We are interested in the politics of one country, but attempt to understand it as an example of how all countries, or all democracies, or all developing countries, etc., operate. We survey 1,500 Americans about their political attitudes, but seek to understand how all Americans or all people form attitudes. Quantitative social scientists usually leave it to historians or intensive qualitative researchers to analyze particular speeches supporting a policy and focus instead on the percent of all speeches that support the idea. Applying a simple classify and count approach yields accurate category percentages under a perfect classifier. Perfect classifiers are unrealistic in real applications. Hand 2006. But they are unnecessary for aggregate accuracy if individual level errors cancel. However, choosing a classifier by maximizing the percent correctly classified can sometimes increase the bias of aggregate quantities, unless the one is careful in training the classifier. For example, the decision rule war never occurs accurately classifies country year dyads into war, no war categories with over 99% accuracy, but is misleading for political science research. Similarly, the proportion of email you receive that lands in your spam folder is a biased estimate of the percent of spam you receive overall, because spam filters are tuned to the fact that people are more annoyed when they miss an important email than when some spam appears in their inbox. This is easy to fix by tuning your spam filter to avoid the bias or correcting after the fact, but we usually do not know the classifier's bias. For example, a method that classifies 60% of documents correctly into one of 8 categories might be judged successful and useful for classification. For example, if Google or Bing were to provide relevant results in 60% of searches, which is about the 2019 average empirically, we might be quite satisfied since the low cost of misclassification is to merely choose another search term and try again. However, because the individual category percentages can then be off by as much as 40 percentage points, the same classifier may be less useful to the social scientist interested in learning about aggregate behavior. The tasks of estimating category percentages quantification or classifying individual documents classification both begin by analyzing a small subset of documents with usually hand-coded category labels. Classification methods normally require these labeled and unlabeled document sets to be drawn from the same population, so the class probabilities can be calibrated. Commonly, however, the labeled set is created in one time period, and a sequence of unlabeled sets are collected during subsequent time periods, each with potentially different distributions. For example, scholars may hand-label a set of social media posts about a presidential candidate into the 10 reasons people do or do not like this person. Then, for each day after the hand-coding, a researcher may try to estimate the percent of posts in each of these categories using the initial hand-labeled set, with no new coding of documents. The methods of quantification we discuss here are designed to accommodate these situations, even though these are the circumstances where the assumptions behind classification methods are violated. We build on the only non-parametric quantification method developed for estimating multi-category proportions that does not resort to individual classification as a first step. This methodology was developed in King and Liu 2008 with survey research applications in public health, and in Hopkins and King 2010 with applications to text analysis in political science, and it was extended in King Liu, and Shibuya 2010, and King Pan, and Roberts 2013 Appendix B with a U.S. patent issued for the technology, King, Hopkins, and Liu, 2012. Over 2,000 scholarly articles in several scholarly fields have cited these works according to Google Scholar. The method has come to be known by the name REDME, which is the widely used open-source software that implements it. Hopkins, King, Knowles, and Melendez, 2013. We begin by developing the intuition behind REDME's non-parametric methodology and highlight situations where it can be improved. We then outline an approach for improving performance via two techniques, both of which involve better representing the meaning of the text. First, our technique allows for changes in the meaning and use of language over time by adapting matching techniques developed from the causal inference literature. Second, we develop an algorithm that chooses a feature space to discriminate between categories with as many non-redundant or independent features as possible. We summarize the REDME estimator and its assumptions in Section 2. Section 3 then introduces our new methodology. In Section 4, we compare our approach to REDME in out-of-sample empirical evaluations in 19,710 datasets, derived from subsets of 73 corpora, and repeated with 18 different evaluation protocols. We discuss what can go wrong and how to avoid it in Section 5. Our approach will not necessarily perform better in every dataset. The ping-pong theorem applies here too. Hoadley 2001. But in unusually extensive empirical tests, we find it normally outperforms other approaches in real data, under the real-world conditions we describe below. Section 6 concludes, proofs, simulations, illustrations, and other supporting information appears in the supplementary appendices. REDME, estimation without classification. We now describe REDME, laying the groundwork for our subsequent improvements. Figure 1 gives a schematic summary that may help guide the discussion as we introduce each component. Notation. Consider two sets of textual documents, L, which includes N superscript L documents labeled with a category number, and U, which includes N superscript U, unlabeled documents, where N equal to N superscript L plus N superscript U. When there is no ambiguity, we use I as a generic index for a document in either set, and N as a generic description of either set size. Each document falls into category C in a set of mutually exclusive and exhaustive categories C in CC, but the category label is only observed in the labeled set. We write D sub I equals C to denote that document I falls into category C. Denote N sub C superscript L equals the sum from I equals 1 to N superscript L of the indicator that D sub I equals C as the number of documents in category C in the labeled set, N sub C superscript U as the unobserved number in C in the unlabeled set, and N sub C generically for either set in category C. The proportion of unlabeled documents in category C is Pi sub C superscript U equals the mean over I in U of the indicator that D sub I equals C, where for set A with cardinality number sign A, the mean over I of function gi is the mean over I in A of g of I equals 1 over number sign A times the sum from I equals 1 to number sign A of g of I. The vector of proportions. Pi superscript U is defined to be the set pi sub 1 superscript U. Pi sub C superscript U, which represents our quantity of interest, forms a simplex, that is, pi sub C superscript U is in 0, 1 for each C, and the sum from C equals 1 to C of pi sub C superscript U equals 1. We also define the analogous but observed category proportions for the labeled set Pi superscript L, text to numbers. In this first step, we map the entire labeled and unlabeled corpora, with the document as the unit of analysis, into a constructed space of textual features with the definition of the rows taking the place of the unit of analysis, a choice to be optimized. Many ways of performing this mapping can be created. We propose one optimized for quantification. For REDME, Hopkins and King 2010 begin with a set of K unigrams. each a binary indicator for the presence coded 1 or absence 0 of a chosen word or word stem in a document. The number of possible strings of these zeros and ones, called a word stem profile, is W equal to 2 to the power k. The readme approach then computes a W by one feature vector, denoted S superscript L, by sorting the labeled documents into the W mutually exclusive and exhaustive word stem profiles, and computing the proportion of documents that fall in each. To make the definition of S superscript L equals open curly brace S superscript L, sub W close curly brace more precise and easier to generalize later, begin with the N superscript L. By W document feature matrix F equals open curly brace F sub IW close curly brace with rows for documents, and columns for features which in this case are unique word stem profiles. Each element of this matrix, F sub IW, is a binary indicator for whether document I is characterized by word stem profile W. Then elements of S superscript L are column means of F. S superscript L sub W equals the mean over I in L of parentheses F sub IW parentheses. Then the same procedure is applied, with the same word stem profiles, to the unlabeled set, which we denote S superscript U. We also define a W by one conditional feature vector as X superscript L sub C equals open curly brace, X superscript L sub WC close curly brace, which results from the application of the same procedure within category C in the labeled set, and X superscript U sub C equals open curly brace X superscript U sub WC close curly brace within category C in the unlabeled set. X superscript U sub C is unobserved because C is unknown in the unlabeled set. These can be computed from F superscript C, a document feature matrix representing only documents in category C. We then collect these vectors for all categories into two W by C matrices. X superscript L equals open curly brace X superscript L sub 1 comma X superscript L sub C close curly brace, and X superscript U equals open curly brace X superscript U sub 1 comma X superscript U sub C close curly brace respectively. Assumptions. We require two assumptions. First, because the unlabeled conditional feature matrix X superscript U is unobserved, assume X superscript L equals X superscript U. Equation 1. Although assumption 1 is quite restrictive, we can relax it. We begin by supposing that the documents in L are drawn from the same distribution as U, which is equivalent to the assumption necessary for individual classification. It turns out we can relax this further. In README, we could assume that the conditional distribution of features given categories is the same, which is much less restrictive. But we go even further and avoid specifying the full probabilistic model entirely by assuming only that the conditional expectation is the same. Or in other words, that the labeled conditional feature matrix is an unbiased estimator of the unlabeled conditional feature matrix. That is, we replace assumption 1 with F applied to X superscript L equals X superscript U. Equation 2. Second, we must assume that matrix X superscript L is of full rank, which translates substantively into A feature choices with W greater than C and B the lack of perfect collinearity among the columns of X superscript L. Assumption A is easy to control by generating a sufficient number of features from the text. Assumption B is only violated if the feature distributions in documents across different categories are identical, which is unlikely with a sufficient number of coded documents. We prove below that high but not perfect collinearity, which can result if categories are weakly connected to the features, or documents are labeled with error, can exacerbate the bias of the README estimator. Estimation. Our goal is to estimate the vector of unlabeled set category proportions. Pi superscript U equals open curly brace pi superscript U sub 1 comma pi superscript U sub C close curly brace given S superscript L, S superscript U, and X superscript L. Begin with an accounting identity. That is, true by definition. S superscript U sub W equals the sum from C equals 1 to C of X superscript U sub WC times pi superscript U sub C for all W, or equivalently in matrix form. S superscript U equals X superscript U times pi superscript U. Equation 3, which is a linear regression, but where the linearity is a property rather than assumption. Then, README estimates pi superscript U by the least squares estimator, pi hat superscript u equals open parentheses x superscript L prime times x superscript L close parentheses to the -1 power times x superscript L prime times s superscript u. Equation 4, or a modified version that explicitly uses the simplex constraint. Properties. In the classic errors in variables linear regression model, with random measurement error only in the explanatory variables, least squares is biased and inconsistent. However, in REDMI, the dimensions of x superscript L remain fixed as n superscript L grows, and so assumption 2 also implies measurement consistency. The limit as n superscript L approaches infinity of x superscript L equals x superscript u. This means that the REDMI estimator in equation 4, which is also a linear regression with random measurement error in the explanatory variables, is statistically consistent as we gather and code more documents for the labeled set and keep w fixed, or at least growing slower than n. Its estimator converges to the truth. The limit as n superscript L approaches infinity of pi hat superscript u equals the limit as n superscript L approaches infinity of open parentheses x superscript L prime times x superscript L close parentheses to the -1 power times x superscript L prime times s superscript u equals open parenthesis x superscript u prime times x superscript u close parenthesis to the -1 power times x superscript u prime times s superscript u equals pi superscript u. This is a useful result suggesting that, unlike classic errors in variables, labeling more observations can reduce bias and variance. It also suggests that, to improve REDMI, we should focus on reducing finite sample bias rather than consistency, which is already guaranteed. Improvements. We outline issues that affect REDMI's performance conceptually in section 3.1. and analyze them mathematically, along with proposed solutions, in section 3.2. 3.1 issues to address REDMI is affected by 3 issues that arise in practice. First is a specific type of concept drift, Gamma et al., 2014, that we refer to as semantic change, the difference in the meaning of language between the labeled and unlabeled sets. Authors and speakers frequently morph the semantic content of their prose to be clever, get attention, be expressive, curry political favor, evade detection, persuade, or rally the masses. For these or other purposes, the content, form, style, and meaning of every symbol, object, or action in human language can always evolve. We address 2 types of semantic change that impact REDMI: emergent discourse, where new words and phrases, or the meanings of existing words and phrases, appear in the unlabeled set but not the labeled set, and vanishing discourse, where the words, phrases, and their meanings exist in the labeled set, but not the unlabeled set. Russian election hacking following the 2016 U.S. presidential election is an example of emergent discourse, language which did not exist a few years before, whereas Russian communism is an example of vanishing discourse, a usage that has been disappearing in recent decades. However, emergent and vanishing discourse can reverse their meanings if the researcher swaps which set is labeled. For example, in analyzing a large historical dataset, a researcher may find it more convenient to read and label a contemporary dataset and infer to the historical datasets, e.g. as they are recovered from an archive, to label documents at the start of the period and infer to subsequent periods, or to code a sample spread throughout the period and to infer to the full dataset. Either vanishing or emergent discourse can bias REDMI, but only if such discourse is present in a specific way we describe below across the categories. Second is the lack of textual discrimination, where the language used in documents falling in different categories or across features is not clearly distinguishable. For clarity, we divide textual discrimination into 2 separate concepts that, in the REDMI regression, are related to the minimal requirement in least squares that, to reduce variance and model dependence, X must be of full rank and ideally far from degeneracy. Since X represents categories as variables and features of the text as rows, we refer to these 2 variables as category distinctiveness and feature distinctiveness respectively. The lack of textual discrimination may arise because the conceptual ideas underlying the chosen categories or features are not distinct. Hand coding errors can also lead to this problem, which is commonly revealed by low levels of intercoder reliability. The problem can also occur because of heterogeneity in how authors express information or a divergence between how authors of the documents express this information and how the analyst conceptualizes the categories or codes. The features. Also common is where the analyst begins with distinct and well-defined conceptual definitions for the set of C categories, with examples of documents that fall unambiguously into each one, but where it turns out upon large-scale coding that large numbers of documents can only be described as falling into multiple categories. Adding categories to represent these more complicated expressions, so that the resulting set is still mutually exclusive and exhaustive, is a logical solution. But this step often leads to a more cognitively demanding hand-coding problem that reduces intercoder reliability. A final problematic situation for REDME occurs due to interactions with the other two problems. This issue is proportion divergence, when the category proportions in the labeled set PIL diverge from those in the unlabeled set PIU. To understand this issue, consider a data set with massive semantic change and no textual discrimination, so the document texts are largely uninformative. But where L approximately equal to, such as when the labeled set is a random sample from the unlabeled set. In this situation, REDME will return the observed proportion vector in the labeled set L, which is a good estimate of U. This means that we can sometimes protect ourselves from semantic change and the lack of textual discrimination by selecting a labeled set with a similar set of category proportions as the unlabeled set. This protective measure is impossible to put into practice in general, as it requires a priori knowledge of category membership, but it can be useful in some cases when designing training sets, and we show below that it can be corrected for. Analytical solutions. We now propose improvements to REDME, including 1. A dimension reduction technique for direct estimation of category proportions, analogous to techniques that have been used for improving classifier performance, e.g. Brunzel and Erickson 2000, Vincent et al. 2010, and 2. An adaptation of matching methods for causal inference. We also show in Appendix D how the methods developed here may have uses in the causal inference literature. Figures 2 gives a schematic summary of Step 1, and Figure 3 summarizes the whole algorithm including Step 2. Dimension reduction is especially important here because numerical representation of text documents can have an outsized impact on the results. See Denny and Sperling 2016, Levy, Goldberg and Dagan 2015. The idea behind our dimension reduction approach is that even if large numbers of individual features perform poorly, lower dimensional linear combinations of features may do considerably better. We begin with the N by W document feature matrix F defined in Section 2. Our goal then is to project this matrix to a lower dimensional N by W prime. Document feature matrix F equals F times gamma, where gamma is a W by W prime matrix of transformation weights defined below, and W prime is much less than W. Once we obtain F, we can take conditional expectations of the features given the category labels to generate the REDME regression matrix as before. We denote conditional regression matrix obtained from F as X, in parallel to notation F and X. The key question then is how to define gamma to choose among the many possible lower dimensional F matrices and thereby reduce REDME's bias. To answer this question, we develop intuition by studying REDME's bias in simplified data with only two categories. Because of the simplex constraint, the unlabeled set category proportions can then be characterized by a single parameter, pi superscript u sub 1. The accounting identity for each feature mean W, S superscript U sub W, can be written as S superscript U sub W equals X superscript U sub W2 plus B superscript U sub W times PI superscript U sub 1, where B superscript U sub W equals X superscript U sub W1 minus X superscript U sub W2. Equation 5 quantifies the systematic component of textual discrimination between the two categories. The REDME estimator is then the least squares estimator of pi superscript U sub 1. Proposition 1. The two-category REDME estimator is pi hat superscript U sub 1 equals fraction open summation from w equal to W of B superscript L sub W times parenthesis S superscript U sub W minus X superscript L sub W2 parenthesis close over summation from w equal to W of parenthesis B superscript L sub W, parentheses squared. If X superscript L equals X superscript U, the above expression equals pi superscript U sub 1 and REDME is unbiased. We can relax this assumption by making assumption 2. which we express as x superscript L sub WC equals x superscript U sub WC plus epsilon sub WC, where epsilon sub WC is a random variable with mean 0 and variance inversely proportional to n sub c. We then write the readme estimator in terms of x superscript U, the true unlabeled set category proportion pi superscript U sub 1, and the sample category size n superscript L sub c, which we can use to obtain the approximate bias. Proposition 2. The approximate bias of the readme estimator is bias of parenthesis pi hat superscript U sub 1. Parenthesis approximately equals fraction open summation from equal 2 to W of bracket VR of parenthesis epsilon sub W2, n parenthesis minus QOV of parenthesis epsilon sub W1 comma epsilon sub W2, end parenthesis bracket times parenthesis 1 minus pi superscript U sub 1 parenthesis minus bracket VAR of parenthesis epsilon sub W1 end parenthesis minus QOV of parenthesis epsilon sub W1 comma epsilon sub W2 end parenthesis bracket times pi superscript U sub 1 close over summation from equal 2 to W of bracket parenthesis B superscript U sub W parenthesis squared plus var of parenthesis nu sub W end parenthesis bracket, with combined error variance nu sub W equals epsilon sub W1 minus epsilon sub W2. Proposition 2 suggests several factors to consider when defining gamma. As the systematic component of textual discrimination, B superscript U sub W increases relative to the variance of the error terms, epsilon sub W1 and epsilon sub W2. The bias approaches 0. In other words, readme works better with distinct language across categories. We should therefore define gamma to maximize category distinctiveness, CD, the difference in conditional means across categories. We do this by directly generalizing to C categories equation 5, CD of parenthesis gamma close. Parenthesis is proportional to summation over C less than C prime of summation, from equal 2 to W prime of the absolute value of parenthesis x, superscript L sub WC minus x, superscript L sub WC prime, parenthesis, where the inequalities in the summations prevent double counting. This expression is simply the sum of all the absolute value of all the B superscript U sub W terms. Proposition 2 also suggests defining gamma to increase feature distinctiveness FD, which involves making the rows of our regression matrix X closer to independent. To see why, consider how the numerator of the approximate bias contains the sum across all the features of the difference in the differences between the error variance of the categories and the covariance between the error variances. We can call this latter difference excess variance. If the features all were to capture the same latent quality, we would encounter a situation where the differences in excess variance would tend to go in the same direction, either all positive or all negative across the features. Dependencies between one feature and another would drive the bias far from 0. However, when the features capture distinctive latent qualities of the text, the difference is in excess variance between the categories will sometimes be positive and sometimes negative, so their sum will be closer to 0. We define this criterion in parallel to CD as FD of gamma is proportional to the sum from CC less than CC prime of the sum from WW prime less than WW of the absolute value of X superscript L sub WC minus X superscript L sub WC prime minus X superscript L sub W prime C minus X superscript L sub W prime C prime, where again the inequalities in the summations prevent double counting. We then choose gamma by optimizing both CD and FD. Gamma star equals ARG max over gamma in R to the power W by W prime of parenthesis CD of gamma plus FD of gamma parentheses. As Appendix B demonstrates, using only one of these two criteria alone does not optimize as desired. Thus, although we can apply README in any feature space summary of the documents, using the lower dimensional feature space defined by gamma should reduce bias in README. Adapting matching methods for text analysis. Finally, we add one last insight by considering the special case of independence of measurement errors across categories. That is, COV of parenthesis epsilon sub W1 comma epsilon sub W2 end parenthesis equals 0. In this situation, readme bias is minimized when the following relationship holds between the labeled and unlabeled set category proportions. Proposition 3. When measurement errors are independent across categories, the bias of readme is minimized at pi superscript L sub 1 equals fraction open, pi superscript U sub 1 times, summation from equal 2 to W of sigma, sub W1 squared close over pi superscript U sub 1 times, summation from equal 2 to W of sigma, sub W1 squared, plus parentheses 1, minus pi superscript U, sub 1 parentheses times, summation from equal 2 to W of sigma sub W2 squared. Thus, when the measurement error variances are roughly equivalent across categories, the bias of readme is minimized when proportion divergence is smallest. We use this result to simultaneously reduce the biasing effect of vanishing discourse and to reduce proportion divergence. We do this borrowing the idea of matching from the causal inference literature. Ho, Imai, King, and Stewart, 2007, Iakis, King, and Poro, 2012. In causal inference, matching prunes control observations from the data that have covariate values far from treated observations. In our case, we fix the unlabeled set and selectively prune the labeled set to remove documents with covariate profiles far from those in the unlabeled set. To implement this idea, we search the labeled set L for a matched subset, M, that more closely resembles the unlabeled set. We do this without any information from the category labels since they are unobserved in the unlabeled set. The goal is to remove observations from the labeled set that are so far in their content from the observations in the unlabeled set that they likely come from an entirely different data-generating process. If the text of the documents are meaningful, exact one-to-one matching of documents in this way will eliminate all error, since it will mean that we have a hand code for each unlabeled document. In practice, approximate matching is usually needed, and any labeled unmatched documents are pruned and not used further. Our matching is in a space of the transformed word vector summaries, designed for our specific problem. Aligning the space of matching and the goals of the analysis are of course also key in matching for causal inference. King and Nielsen, 2017. Finally, we recompute F underbar and the matched X underbar L, which we denote X underbar L sub M, and apply the readme regression. As a result, the assumption in equation 2 now needs only to hold in the matched subset of the labeled set, rather than for the entire labeled set. The expected value of X underbar L sub M equals XU. Matching thus considerably weakens the assumptions necessary for readme estimation, and predictably reduces its bias. Evaluation. Design. We performed 18 large-scale evaluations of our methodology, each following a different design protocol for allocating documents to membership in the labeled and unlabeled sets. Prior approaches in the literature have almost always used a single evaluation design, as compared to our 18, and only a few datasets compared to our 73. The resulting 19,710 empirical evaluations in our replication data and code thus increases the rigor which future scholars can bring to bear on new methods developed to improve on those proposed here. For each design protocol, we estimate readme 2 and 32 alternative statistical methods that can be used to estimate category proportions, including readme. Each method is analyzed on 19,710, equal to 73 1518 datasets because we have 73 corpora, 15 iterations per corpora per design, and 18 designs. The total number of method design observations is therefore 630,720, equal to 19,710 times 32. The 32 alternative methods of estimating category proportions are of 5 types. The first 4 types comprise 6 classifiers each run within each of the 4 possible combinations of A, a discrete or continuous feature space, and B, a classification of whole documents and counting or averaging. Continuous probability estimates to yield estimates of the category proportions. The 6 classifiers include support vector machines, random forests, naive Bayes, and L1 and L2 regularized multinomial regression, using standard settings and described in James, Witten, Hasty, and Tibshirani 2013, and an ensemble of these classifiers based on an average of classifiers within each of the 2 cells of B. The 5th type of alternative method includes 8 methods tuned for quantification. Among these, only readme is designed for more than 2 categories. We adapt the remaining 7, Friedman, adjusted counts, HDX, median sweep, mixture HPMF, mixture L1, and mixture L2, each detailed in Feirat 2016, to multiple categories via estimation of repeated dictimizations of the set of categories. When a method has adjustable parameters, we either optimized over them or used the software default. Each of the 19,710 datasets we analyze, constructed as a subset of one of 73 corpora, has a labeled out-of-sample test set that plays the role of the unlabeled set, except that we are able to use its labels after estimation to evaluate performance. The 73 corpora include 3 used in Hopkins and King 2010, 1,426 emails drawn from the broader Enron Corporation corpus made public during the Federal Energy Regulatory Commission's investigation of the firm's bankruptcy and hand-coded by researchers into 5 categories. 2. A set of 462 newspaper editorials about immigration, with 3,618 word stems and 5 categories. And 3. A set with 1,938 blog posts about candidate Hillary Clinton from the 2008 presidential election, with 3,623 word stems and 7 categories. We also include 11,855 sentences, with 5 categories and 3,618 word stems from the Stanford Sentiment Tree Bank, Socher et al. 2013. Finally, we include 69 separate social media datasets, most from Twitter and a few from diverse blogs and Facebook posts, each created by a different political candidate, private company, nonprofit, or government agency for their own purposes, covering different timeframes and categorization schemes. See Farad 2016. These data cover 154,200 word stems, 312 categories, and 704,000 tweets. All data are in our replication dataset, except that for privacy reasons, the raw text of the last set has been coded as numbers. Nearly all documents in the 73 corpora are labeled with a timestamp. For the empirical design, we randomly select a time point and pick the previous 300 documents as the labeled set, and the next 300 documents as the out-of-sample evaluation set, wrapping in time if necessary. For each corpora, we repeat this process 50 times. This procedure keeps the evaluation highly realistic, while also ensuring that we have many types of datasets with variation in proportion divergence, textual discrimination, and semantic change. The joint distribution of these quantities is crucial in determining the overall error dynamics, so accurately simulating this distribution is of the utmost importance in this exercise. Although the empirical design emphasizes realism about what we see in practice, we replicate this analysis across the 18 designs described in Table 1, which make different assumptions about the joint distribution. Each of the 18 evaluation designs offers a different way of generating 19,710 datasets as subsets of the 73 corpora described in Section 4. Each dataset is divided into a labeled set as well as a test set that serves the purpose of the unlabeled set during estimation, but can also be used for evaluation since all its document labels are observed. Implementation details for word embeddings. We use the 200-dimensional global word vector GLOVE model, estimated from about 2 billion Twitter posts, with a vocabulary of about 1.2 million terms. We follow standard approaches by summarizing the vectors, in our case with the 10th, 50th, and 90th quantiles of each dimension Templeton and Kalita 2018, resulting for any given corpus. In F with W equal to 203 equal to 600 unique features observed for each document. Because we are optimizing over these factors, we do not require the pre-processing steps for textual data, removing stop words, punctuation, etc. Instead, we are only constrained by the choice of the pre-processing for the original word embedding training, which in the case of GLOVE means making the text all lowercase. For optimization, we use stochastic gradient descent with momentum, minimizing overfitting with dropout, gradient clipping, normalizing F to mean 0, and variance 1, and using a standard confidence penalty. King, Gebbie and Malosh 2019, Kingma and BA 2014, Pereira et al. 2017, Srivastava et al. 2014. We set the number of final features, W, to 20, although performance does not greatly depend on this parameter, as long as it is much smaller than the number of input features W. Results. We present results across our numerous evaluations in 3 ways. First, Figure 4 compares the performance of README 2 to the 32 alternative methods across all 18 designs. For each method, we compute the proportion of datasets with higher error than README 2 vertically by the proportion divergence in quantiles horizontally. Our new approach outperforms the best classifier in these data, a support vector machine SVM model run in the continuous feature space in 94.5% off corpora. Many of the 32 methods are outperformed by REDMI 2 in 100% of the cases, as indicated by appearing at the top of the graph. Relative performance remains excellent across the different levels of category proportion divergence between labeled and unlabeled sets. The new method's relative performance improves when proportion divergence is high at the right, with more substantial changes between labeled and unlabeled sets. Which makes sense, since ours is the only approach to directly address semantic change. The different types of methods, represented as lines, follow three basic patterns in relative performance. Classifiers with averaged probabilities, in black and green, have higher SAE relative to REDMI 2 as divergence increases, due to their assumption that test and training sets are drawn from the same distribution. B quantification methods, in light blue approach, REDMI 2's performance only with high levels of divergence, since they are designed for this situation, and C, the remaining methods perform relatively poorly overall, regardless of the proportion divergence. Second, we provide a more detailed comparison of the performance of REDMI to REDMI 2, the primary goal of this paper. In the empirical design, which we argue is particularly important in practice, we find an 35.3% average corpus-wide improvement over REDMI, which in terms of SAE is a substantial 9.4 percentage points. Figure 5 plots estimation error vertically for REDMI compared to our new approach, ordered horizontally by size of the improvement. The length of each arrow represents the average improvement over subsets of each of the 73 corpora, with one arrow for each. In all cases, the arrows face downward, meaning that in every corpus our new method outperforms REDMI on average. Our new approach performs better in all three of the datasets used in Hopkins and King 2010, and also the Stanford Sentiment dataset, the colored arrows. Next, we show that our results are robust across our 18 diverse simulation designs described in Table 1. The left panel of Figure 6 compares average performance over simulations, and reveals that REDMI 2 outperforms REDMI for every simulation design 1, as indicated by being above the dotted horizontal line. The empirical analysis noted in red is the substantively most meaningful design described above. Then, the right panel of Figure 6 illustrates how, across the 18 simulation designs, REDMI 2 outperforms not only REDMI, but all 32 alternative methods in a large fraction of cases. REDMI 2's average rank is 3.89, whereas the next best algorithm's average rank is 6.50. Median performance, indicated by the horizontal gray bar for each design, is always improved. We performed a final check to assess the sensitivity of our analysis to the vector representation of the words. We reanalyzed the Clinton blogs data using a labeled-unlabeled split from our empirical design. We generated the quantification tune features USNG, the 200-dimensional glove embeddings from Twitter, used in our main simulation results. We then generated features using 25 and 100-dimensional glove embeddings from Twitter, as well as the 50-dimensional embeddings trained on a 2014 Wikipedia corpus. We find that each of the 20 synthetic features from the 200-dimensional glove embeddings have close counterparts in each of the other cases. The maximum absolute correlation for each feature is above 0.600, and most are above 0.80. These results, illustrated in Figure 7, show that the REDMI 2 algorithm described here is quite robust to the choice of vector representation for the words. The random line in blue indicates the density of maximum absolute correlations. We would see if there were no relationship between the transformed 200-dimension Twitter vector summaries and the transformed summaries from other vector sources. In sum, our new methodology would seem to be preferably to REDMI and other existing methods across a wide array of corpora, datasets, and evaluation protocols. It is also worth noting that REDMI 2 is computationally fast due to its use of batch sampling and efficient symbolic math libraries. Estimation on a dataset with a labeled set size of 1,000 and an unlabeled set size of 500, with 5 categories and 600 raw features, takes about 11.5 seconds on a CPU with a 2.7 GHz processor and 8 GB of memory, while estimation via SVM, for example, takes 10.5 seconds, and via lasso regularized regression takes 7.3 seconds. Current issues and future research. The methods introduced here appear to be clear improvements over REDMI and other approaches in a wide variety of circumstances, category types, and datasets. We focus in this section on the 3 situations where our approach may not help, and further research may be productive. In addition, increasing computational power and data availability may open up the possibility of other improvements, such as by optimizing over fixed choices we have made or, for example, simultaneously training word embeddings with our approach. First, when we use matching in continuous space, we generally reduce proportion divergence and the effects of vanishing discourse. However, emerging discourse not only can cause bias in any method, but this bias can sometimes be induced by the analyst in the process of dealing with vanishing discourse. In addition, although REDME2 is the only method that has been proposed to reduce the effects of vanishing discourse, it is of no help if all the relevant discourse vanishes within a category. This is akin to a violation of the common support assumption in causal inference, and so must rely on risky extrapolations. Unlike with classifiers, our methodology does not need to assume that the labeled and unlabeled sets are drawn from the same distribution, but we do require that the conditional distributions have some overlap. If one suspects that meaning or language is changing dramatically, the easiest fix is to code additional observations from later points in time. Second, if the original feature space is highly sparse, as in a regression with a large number of irrelevant covariates, then our optimization algorithm may have difficulty arriving at a stable solution for gamma. This can happen with highly uninformative text, categories with labels that may be more meaningful to investigators than the authors of the text, or error-ridden hand coding. If the word vectors used to generate the raw features were trained on an inappropriate corpus, performance would also be expected to deteriorate, as the relationship between the text and numbers would be more tenuous. Our word vectors are from Twitter, and so we recommend swapping these out with another set if the text being analyzed differs substantially from tweets. Fortunately, many types of pre-trained word vectors are now available, including in many languages. Finally, our approach relies on meaningful text in each document, conceptually coherent and mutually exclusive and exhaustive categories, and a labeling effort that validly and reliably codes documents into the right categories. These may seem like obvious criteria, but they always constitute the most important steps in any automated text analysis method, including ours. In our experience, most of the effort in getting an analysis right involves or should involve these preliminary steps. Concluding remarks. We improve on REDME, a popular method of estimating category proportions, which is a task of central interest to social scientists and others. We do this without having to tune or even use the often model-dependent methods of individual classification developed for different quantities of interest. We prove properties and provide intuition about REDME, and then build our alternative approach. We have tested our analysis in 73 separate datasets, 19,710 data subsets, and 18 evaluation protocols, with encouraging results. Overall, our approach weakens the key assumptions of REDME while creating new, more meaningful numerical representations of each of the documents specifically tuned to reduce the mean square error of multi-category. Nonparametric quantification. We can identify several ways of building on our work to further improve performance. These include methods for optimizing the raw continuous textual representations used in REDME2. In this analysis, we use document-level summaries of word vectors for the raw features, but there is no quantitative principle implying that this choice is optimal and so could be improved. Indeed, our results suggest that the quantitative features used in REDME greatly improve performance. It is natural, then, to consider continuous document-level representations directly from the labeled and unlabeled sets, or possibly using category-wise information from the labeled set, or with smoothing toward word vectors created from giant corpora such as that we use from Twitter. With these additions, the estimation process could be more fully optimized for quantification. Finally, further work could explore more systematically the application of these ideas to other nonparametric methods,